Board here. So again, thank you for coming. My name is Mark Phillip, and I'm an application engineer with Studica Incorporated. And Studica is a software and hardware reseller for all sorts of products, and we primarily deal with schools in K through 12 and higher education in North America. And we deal a lot with public and private schools, and we've been doing this for a little over 30 years, so we have a lot of experience. And today we're going to be looking at the Internet of Things. We're going to talk a bit about what it is, why it's important, how we think we can bring this into schools by using the fischertechnik robot sensor IoT station. So we're going to take a look at that. We'll talk a little bit about what fischertechnik is. I don't think the presentation should take too long. This is the first time I've actually done this particular one, so I'm looking at roughly 40 minutes or so, I think, to get through this. My contact information is markp@studica.com, and our website is www.studica.com. All right, so first of all, what is IoT? Some people might know what it is, others maybe not. I know it's kind of a buzzword. A lot of people hear about the Internet of Things, but I feel like a lot of people don't really know how to define it. Wikipedia defines it as a network of physical devices, vehicles, home appliances, other items embedded with electronics, software, sensors, actuators, and connectivity, which enables these things to connect, collect, and exchange data. I think a simpler way of putting it is to basically say it's a bunch of devices connected together, sharing data for some reason or some purpose. So examples of this that we see currently in our lives are wearables. Specifically, I like looking at the pedometers, like the Fitbit, for instance, because I think this is a very clear-cut example of what IoT is. Your Fitbit, the device that goes on your wrist, all it is basically a bunch of sensors. And those sensors are collecting data about your velocity and the rotation of your arm and all these things. And based on that data, there's some computation that's detecting or basically predicting how many steps you've taken based on that data. And when you use your application on your phone to access your Fitbit, what it's doing is basically pulling that data from the device. So the Fitbit itself isn't really, all it is basically a couple of sensors with like a Bluetooth connection or some kind of network card that can connect to the internet or Wi-Fi, which enables your phone to be able to grab that data. So this is a very simple example of how data is shared between two devices to accomplish something. And when we scale that out, we start getting into the realm of things like smart homes, right? Think back to the Jetsons or like the 1950s, the home of the future or whatever, where you have an automated home that does everything for you. That's the idea of a smart home, and that relies on the Internet of Things. It relies on all these components in your house corresponding with each other and coordinating their functionality. And we also see things like connected cars, which is a big push in the automotive industry right now, especially with like smart cars, like the AI cars, the ones that drive themselves. They need data from multiple points of reference in order to accurately run their algorithms. So I like to always present some statistics about these fields to kind of give some context about, you know, what's going on with this field, where is it going, where has it been. So first of all, we want to look kind of at how many connected devices are there currently versus how many are we projecting in the next 10 years. There's been a lot of research in this area. One of the sources I found was Statista, who did a very comprehensive research on the industry. And currently there's roughly 15.4 billion devices that are connected in some way as far as the IoT is concerned. By 2025, they're expecting 75.4 billion devices. That's roughly a 5 times increase in 10 years. That's pretty massive. And the curve starts to almost look slightly exponential as it goes on. So basically what we're looking at is a massive increase of IoT devices in the next years. And with this massive increase in devices, there comes a larger pool needed of skilled specialists who can work on these devices and know how to manage this infrastructure. Now, who's using all these devices? A lot of people might think it's consumers because that's what we see all the time, right? We see people with pedometers and they have their Teslas that are borderline smart cars, self-driving, right? You see all these technologies in the consumer world that seem to be connected, seem to be doing this. However, the reality is that most of the IoT is actually being used in business and manufacturing and healthcare, like almost overwhelmingly. that's not to say that the consumer market's not there. It's actually rapidly expanding, especially with stuff like Alexa. Smartphones are becoming more and more enabled. But what we see is in the factory setting, there's all sorts of automation occurring, right? And so when you have a factory that's automated, all these devices in the factory have to communicate with one another, and they have to be sharing data, or else the whole thing doesn't work, right? They have to be very coordinated, very synchronized. And so we're seeing a lot of, I kind of call it local area IoT, where inside of your business, you might have this really comprehensive IoT network that's not necessarily part of the internet. And then in healthcare, we're seeing this big push of things like patient data along with prescription drug checking and like cross-referencing between drug interactions. There's all sorts of research going on about protein synthesis. Lots of stuff in that field that's relying on a lot of different devices sharing data with one another. And so healthcare is really pushing this field very heavily as well. And as far as this distribution goes, most analysis sees this continuing into 2025, with the consumer sector taking a bit more of the chunk as we get more and more devices that are connected. This source is also from Intel, by the way, who did a very comprehensive analysis of IoT as well. So what countries are using IoT? It's overwhelmingly North America and Europe. However, the Asia-Pacific region, which includes China, Russia, they are also a pretty heavy investor. What's kind of interesting about the data is that different regions are adopting more heavily in different sectors. So the one that I point out is the smart agriculture down here, where the Asia-Pacific region is actually more invested than Europe is, which is interesting. It kind of, I don't know what you can infer from that, but it seems like the Asia-Pacific region sees more need for getting IoT involved with agriculture. And an example of that is how they put RFID chips on cows and livestock, right? To basically track them around and make sure that everything's accounted for. So those chips go through RFID readers, which send to some kind of database, which sends to some kind of program that does something, right? That's the idea with IoT, is you have all these different separate entities coordinating together all their data. So again, the chart can be deceptive. It paints a picture that North America and Europe are kind of one of the only spenders, but the Asia-Pacific region is definitely there, and the Middle East and Africa is also incorporating this, just at a smaller rate. Now, the economics of IoT, we want to look at basically the spending here. Like, is this a worthwhile investment? Is this a thing that we want students to be learning, right, for their future? So in 2014, the total spending on IoT was roughly $3 trillion. And I want to be clear about this because I was blown away by this number at first. This is like total spending overall since the start of this technology, right? This isn't like within 1 year, people spent $3 trillion on IoT. To my knowledge, this is cumulative spending, but I couldn't find a specific metric about that from Statista, who put these numbers together. Now, by 2020, they're expecting roughly $9 trillion in spending by 2020, which is massive. That's a 3 times increase in roughly 6 years. And what's kind of interesting is to see what other industries are popping up by 2020. We have construction infrastructure showing up here where it didn't in 2014. Energy and utilities show up, so does retail. Now, Intel projects $6.2 trillion by 2025, so they're a little more conservative in where this number is going. But as with statistics, you'll always get kind of varying projections. Regardless of which one you believe or which one sounds more reasonable, that's still a lot of money, that's still a lot of spending, and that's a lot of investment within a 10-year period into a field where there's going to be a lot of pool for opportunity for people who know this material. Now, how does this spending break down within the world of IoT? And this is where we start talking about specializations for students, right? Like, what kind of fields are they pursuing and what are they studying to prepare themselves for this kind of technological upheaval? The biggest chunk that's being spent for IoT is hardware at 35% of the chunk. So this is going to be all your computer components, your hardware infrastructure, things like that. Connectivity is a big one, so that's things like your wireless networks, networking protocols, probably things like 5G, IT installation services, so this is kind of like your maintenance, so you have IT professionals who can install this and work with it, your software, so all the computer software that takes the information and does some kind of service with it. And then this is known as anything as a service. It comes from the software as a service model, where basically you have some running cost of what you spend to have this service provided to you. Now, the clear takeaway here is that all these fields require educated people, right? Like this, pretty much all these fields are going to require people with degrees or at least certification, technical, trade school kind of background. So in the hardware world, you have computer engineers, electrical engineers, mechanical engineers, civil engineers, really anybody in the engineering realms involved here. Connectivity, you have your network engineers, and software, you have computer scientists, software engineers, right, programmers. IT and installation, you have all of your system administrators, IT administrators, and even with anything as a service, you kind of have, even in the realm of like sales representatives, right, people who are trying to sell these services to people who need it. So the idea here is that this is a huge STEM field that is involved with numerous different professions. So with all this money in here and all this money potential for people who know these skills, like that's a lot of opportunity for students going into the near future here. So that kind of brings us to, why is learning IoT important? There's some obvious ones from that data, which is that there's a lot of highly paid work, right? There's a lot of opportunity there that needs to be filled as this investment becomes massive all over the world. So it's a matter of preparing students for that future, but then even taking a step back from the money aspect, it is a new field, and there's a lot of new research here and a lot of new technology, which is really fun and exciting. And students who are into this kind of stuff, this is a place where they can really make an impact. There's a lot of opportunity to really innovate and solve complex and challenging and also unique problems that students might find interesting. So there's a lot of reasons to really be learning IoT, and probably the most fundamental one to me is that this is going to become a way of life, just like computers have. And getting your students into this up front is going to prepare them to be able to handle this when it becomes as prevalent and intrusive as computers are in our lives in the next 15, 20 years. So that brings us to, how do we want to teach this? And one of the things Studica started offering recently, tongue-tied, is the fischertechnik Robotics Sensor Station IoT, which is a bit of a mouthful of a name. But basically this runs with the fischertechnik components, and the point is that you communicate with this robotics controller here, which is basically an embedded computer, and you can wire your different sensors and motors to this to basically create a sensor station that can do a lot of different functionality. This comes in 2 different sets, and we'll kind of break down the different sets a little bit later. But the main intent here is to introduce students to data logging, the idea of the smart home, which is in general just the idea of the Internet of Things overall. So one of the first things that the kit will go through is basically, how do we work with the fischertechnik components? Because some people might not be familiar with fischertechnik. Maybe this is a little bit new. Mouse button. Maybe this is new to some people, so they include in the guide, like, how do you connect things together? What kind of parts are these? What are these parts used for? To kind of ease you into it so you're not completely lost coming into this. So they go over actuators, sensors, software, what the TXT controller is, and all that. So the first model in the kit that you can build is this lighting sensor station. And the idea here is that we want to use a brightness sensor, so a photoresistor, to detect the light in the room essentially, and then dim or make these lights brighter based on that lighting that's hitting the photoresistor. And so this is a great activity basically to enable students to become familiar with the TXT controller, and it's designed to really take them step by step through the act of creating a program with the Rogo Pro software, which is a visual programming language. And you kind of see right here how you have nodes that go to each other, and you basically create the flow and some of the logic, but you're not doing text programming. So you're getting a lot of the methodology in here, but not necessarily the nitty-gritty syntax of a full-on programming language. But you can use this to interface with the TXT controller and make behaviors happen. So the students, what they're going to do is basically create a program where as the light of the room becomes darker, these lights will turn on. And so the students are going to have to experiment with like a resistance threshold from the photoresistor, right? They're going to have to say if the resistance of the photoresistor is above or below, this level, then we want to turn the lights down or turn the lights up. And what they also end up doing is once they have a grasp on that, they end up making a program that will turn the different lights on depending on, so it'll turn on like one light at a time if the light in the room is less than a number or higher than a number. And so you end up with basically 3 levels of brightness that the lights will turn on and turn off around. So it's a very simple introductory lab to basically get you used to using the kit. And then it goes to a noise sensor, which is, when we say noise sensor, we're talking about sound, so decibel level. And with this lab, the students will utilize a sensor built into the circuit board of the included USB camera. So we see this camera here, connects USB to the controller, and there's actually a microphone on here that we're going to use to basically hear the noise and do something with it. So what the students will end up doing is create a program that measures the loudness of the room essentially, and as different decibel levels are reached, different lights come on, either green, yellow, or red. So green is like your lower level sound, yellow is kind of your middle level, and red is really loud. And so you can get this visual feedback of, like, if I clap my hands next to the camera, I'm going to hit the red, right? Whereas if I'm whispering, I might hit the green. And I just want to show a quick video about this. So this was basically me putting it together in super fast speed. And so I just assemble everything. Notice there's not a whole lot of parts here. It's a pretty quick model to build. And it might look like I'm doing this magically without any help, but there's a guide that comes with the kit that walks you through all this. So I'm referencing that guide as I go through it. And it's very clear with good instructions, good pictures. Didn't really have many issues putting this together. Nothing was too confusing. And then, so I hook up the camera here with the USB. And then once I do that, I wire everything. And the wiring diagram is also included in the kit so that you can see how I need to wire all of the electrical components. And then this is it in action. I don't have sound playing, but basically I'm speaking at a normal speaking voice and just watching the lights turn on and off. So the microphone's here on the camera. And when I'm hitting red is when I'm probably speaking loudly or clapping, and then I'm hitting green when I'm like whispering at it. So very simple example here, and that's kind of what the sensor station ends up looking like, and that's what your students will build with this particular lab. And here's kind of a look at the programming side of it. Basically, this is the first lab that students will use that uses a subroutine, which is what this big old looking kind of circuit diagram here is here on the left. A subroutine is sort of like, if you're familiar with kind of text-based programming, whether it's Python or Java or anything like that, a subroutine is basically like a function or a method in those languages where you create some separate block of code and you're able to take inputs and do some kind of output with it, or take inputs and do some kind of like execute some kind of functionality with it. So the main program's here on the right, and students will make this, and they put the microphone into it. They put the level of decibels they want to monitor into it, so 55, 65, and 75 decibels. And then this thing outputs to the different lights based on the logic that's happening here. So basically we're checking like, oh, is the number we're receiving from the microphone less than this value or greater than the value? If it's the highest it can be, we're going to send the red light on, which is going to come out here and hit the red light. And then this just loops all the time. So the students will end up making this, and fischertechnik provides a basically walkthrough on how to build these, so that you can, so you're not just going into it blind. So beyond that, we also have the wellness sensor station, and basically this is a new component, this green looking square here, and what this will do is basically monitor gas, atmospheric pressure, humidity, air temperature, and so the students will be able to utilize this to basically do some fun things with it. And some of those fun things are we're going to do a frost monitor, a mold monitor, and an air quality station. So with the frost monitor, basically we're going to measure the ambient temperature of the room. And if the temperature falls below, say, 3 degrees Celsius, we're going to turn on a red warning lamp, like right here on the bottom. And an alarm from the TXT controller will go off. So the controller itself will actually make an alarm sound. So it's basically just warning you, oh, it's really cold, there's going to be frost, right? And then there's a second one with the mold monitor. We're basically going to be monitoring the humidity, right? And as we monitor the humidity, if we go like 80% or higher, we send off the warning light, just like we do in the frost module. And then the third one, we're going to be looking at the air quality station, which is kind of a similar idea. We're going to monitor the air quality, and then we're going to turn on these lights depending on what the air quality is. So if we actually have good quality, we're going to have the green on. If we're kind of getting bad, we're going to have the yellow one on. And if you're in California in the summer when the wildfires are happening like I am, you're going to have the red one on all the time because the air is terrible. But that's the wellness station. And then we're going to go on to basically the stationary camera. So with the stationary camera, this one's pretty straightforward. We're going to use the environmental sensor to do some data logging, and then we're going to use the camera to do some motion sensing. And then basically raise an alarm if the motion sensing occurs. And so for the data logging part, we're basically going to be using the built-in brightness sensor, so the photoresistor, to display the data using an oscilloscope on a graph here. So whereas before we were using the data programmatically to, say, turn on a light or turn it off, this time we're actually going to be looking at how we can log this data and then like export it to a CSV file, for instance. Right, so then we can take a CSV file and putting it into, say, Excel and start graphing out our data. And then so that's about it for that. And then the last experiment is going to actually be pretty interesting. What we're going to do is basically take a flower vase and put a flower in it and set it up in front of the wellness station. And the students are going to create a program that measures temperature, humidity, atmospheric pressure, air quality, and brightness. And every 12 hours, what's going to happen is these values are going to be saved into a CSV file. And each day, a photo will be taken with the camera. And then basically the idea is over time, like say a week or something, you collect all your data points from the wellness station, you get your CSV file, and you can have your students start graphing that out. And you can also see visually with the camera kind of how has the flower changed based on all this data that we've collected. So that one's a little bit longer of a lab that you could do over a course of time, but it's an interesting one, I think, that really works with a lot of the different sensors as well as really doing the data logging and data analysis. So then students will also be able to make a barometer, and this one's rather straightforward. Basically, it's going to measure atmospheric pressure, and it's going to point to one of these symbols at the top where there's lightning, rain, cloudy day, or sunny day, and you're basically just going to be using atmospheric pressure to try and figure that out. So yeah, this one's pretty straightforward, pretty simple, but can be fun and interesting, and a good way to teach about atmospheric pressure and, you know, how the weather works based on that. And whoops, clicking the wrong button. And then lastly, we kind of go to the final model, which takes everything that you've been doing and just throws it all into one. So the final model is the complete sensor station with a movable camera. This model uses various forms of data communication. You can use USB cable. You can set up the controller as a wireless access point, or you can set the controller up onto a Wi-Fi network. So you don't actually have to have it connected to your computer this time. You can actually make this, you know, like put it in your backyard or something and monitor it from your computer over Wi-Fi, for instance. So the first program with this station is going to involve using the model as a rotating surveillance camera, and the results are going to be viewable on your computer using the RoboPro software. So students are going to learn how to connect the TXT controller to a PC using Wi-Fi, and then once they do that, they're going to see basically that they can bring the device somewhere away from the computer now and make use of Wi-Fi in an intelligent way so that they can actually maybe monitor something in a different room if they wanted to, or somewhere else on campus if you're at school, for instance. And the second project is going to be an expansion of the first one. So the camera is controlled, but the environmental data is also displayed on the oscilloscope. So we actually start graphing our environmental data now along with the camera. And we're also going to include an alarm with this one. So when the camera registers motion, we're actually going to signal an alarm in the form of this red light here. And then lastly, they're going to basically look at how can we connect this to fischertechnik's cloud service to basically monitor the data through a website. And so you're going to kind of get familiar with how does the cloud work? How can I access this data through my phone, for instance, or my laptop or some other computer, and basically not have to worry about what computer am I accessing this on because it's on the cloud, right? And basically you access the fischertechnik website to do that, and the dashboard's displayed and it shows you all the data. You can control the camera from there. It's really interesting, and this is kind of how it looks. Very simple, but each item here represents like a different sensor from the station that you can look at through the website. And I'm actually going to show you how this works. So I have the sensor station hooked up to my computer. And before I go into the cloud part, I want to kind of just show how it works through RoboPro. So this is the RoboPro software, and I know this might look intimidating, but if you go through the whole kit and you go through all this up to the sensor station, you're going to know what all this is doing, and you're going to know how to build it. And there's German on here because I got this from a sample that fischertechnik had given us. So fischertechnik's a German company, so don't freak out if you don't understand what the words are saying, because I don't know what they're saying either. But on the program, we actually have our panel, which is where we're going to display a bunch of information, and then we have the camera section, which is going to show us basically the camera display. So if I start this, that terrible sound you're hearing right now is the camera centering itself. So it rotates to a full 180, and then it basically goes back to center. And if I turn this on, you can see me sitting in my office chair. And so the camera's over here, and then we're getting a number of other data showing up on the graph. And on the graph we have like the temperature is T, which is in the red, which is 20.5 Celsius, and then H is humidity. I believe M is the atmospheric pressure. I can't remember what variables these are used for exactly. It's more clear on the cloud site. B is your brightness. So if I actually go over and cover up the photoresistor, we see that dip to 0, and then I take it back off and we go back up to 28.1. So you can see the dip in the graph right there as I did that. And we can also control the camera, so I can start turning it right. I may go up and down. I can also turn the alarm on, which is going to turn the red light on as it detects motion. And you can't really see it on my camera, but you can see so you kind of see the red blinking off my hand. That's the light as it detects motion. And we can actually see how the camera is detecting motion in here. So when it goes green, it knows that there's some kind of motion occurring. And I think because of the frame rate, it's kind of a little choppy, but you get the idea. So that's kind of how we look at it on RoboPro. Now what if we look at the cloud site? So what I have to do is actually on the controller, I apologize for the sound, the trash trucks are outside, so they're very loud. On the controller, I start the program, and what it's going to do is the same procedure. It's going to center the camera and everything, and once it's done, it's basically going to send a connection to the fischertechnik cloud site and basically enable me to see everything here through this panel. So we don't see anything yet because it's still sending, and fischertechnik servers, I believe, are in Germany, so the signal has to travel across the Atlantic, so there's a little bit of lag time. So let me click back on the dashboard, and there we go. So So there's some of that lag time where I can click on these buttons and the camera does move rather quickly, but the camera is not updating quite yet, probably because the stream has to be updated. Let me refresh the page though, just to make sure everything's okay. There we go. Yeah, so sometimes you have to refresh a couple times to make sure the connection's steady. And what we can do also is say, like, I could take a picture with the camera and that will get put onto the gallery, and I could actually download this and save it and then open it as a JPEG, and then it keeps it in my gallery up here. And with the data here, we see the brightness curve. So this is the photoresistor, and I can actually view it as a curve or as a single value. So if I view it as a single value, it shows me the percentage brightness, right? And if I cover that up with my hands, we should see it change. Yeah, a little bit of lag time again, because we're sending the data now to fischertechnik. We're no longer just talking to the device on my network, right? So if I click the curve, we can kind of see where I just put my hand over over the photoresistor, right? And if I wanted to, I could download this as a CSV file and open this up in Excel. And here I have my data points that are semicolon separated. And CSV is an interesting format because if you do want to incorporate things like Python or programming into this using text-based programming, CSV plays really well with pretty much every programming language because everything's separated by semicolons. So you can easily create complex graphs and data using stuff like Python to parse this information. So we're basically getting our date, time, and brightness, and all that data is put in here for us. So very easy to just grab that and download it. And then we have the temperature curve, which is showing us the current temperature. Again, I can view a single value. And so I can see the temperature is 22.1 degrees Celsius. One thing that might be interesting is converting this to Fahrenheit, especially for those of us in America. And then we also have current air pressure down here, and we can see the curve if we want to view the curve. And then we have current air humidity, and the same thing. We can view the curve or go to the single value or download the spreadsheet. You can also move these around and kind of organize the dashboard however you want. And that's pretty much how the cloud situation works. So you do have to have an account. So you would come to this website, fischertechnikcloud.com. You would create your own account. You would register the TXT controller to your account, which I believe works off the hardware address of the controller. And then it will know like what controller to listen for. And then your controller has to be connected to the internet to be able to connect to their server. So there's a lot of components here that will help get students familiar with like how do we work with the cloud. And then what's really cool is that since this is a website, I can just open it up on my phone too. I don't have to be on my desktop browser. So I could open up Chrome on my phone or Safari and come to this site and see all my data. So, all right, with that being said, we'll kind of start wrapping up here. That's pretty much it for the Robotic Sensor Station IoT. So I'll point out real quick with the sets, we have two different sets. Oh, whoops. And one of them, this 544625, this one requires the RoboPro software, the TXT controller, and the Accu or power set. So if you don't have these things, if you have these things, this kit you could get and you'll be good to go. So people who maybe have fischertechnik or are familiar with it, you can actually probably just grab this kit and you should be good. However, if you don't have those things, you're going to want to get the kit that includes all those things. So the one that doesn't include all these extra items is $280 starting price, and then the one that does include them is $679 starting price. And so that's pretty much how that breaks down. And at this point, I'll open it for questions. And it looks like I lost somebody, so I'll just go through this and just point out that lastly, we do have extra information about fischertechnik on our website, studica.com. Just do a search for fischertechnik and you can see everything we have. If you have questions about pricing or anything about the program in general, feel free to contact us, sales@studica.com, or you can call us 888-561-7521, Monday through Friday, 9 a.m. to 5 p.m. Eastern Standard Time. And lastly, a follow-up email will be sent out with more information, including a recording of the webinar. So be on the lookout for that. And again, if you have any questions you think of later, do contact us. We'll be more than happy to discuss those questions with you and hopefully give you some answers. So with that, I want to thank everybody for coming and hope you all have a good day. Thank you.